my brilliance was too much for YouTube to handle the first time, so let's try again. This is a pretty difficult section. I didn't fully understand it until I turned 5. We'll do plenty of examples and have time in class for questions, so just do your best and you'll be good as me in no time.
So mathematical induction is a method of proving things in math. It's actually quite prevalent. The closest section to what we're doing in this that we've done in the past is probably a 5.1 because that was all proofs and whatnot. But this is still fairly different. It's probably different from anything else you've done so far in math. Induction is just a two-step process. Basically, what we need to do is if we have a statement, we need to prove that it's true for n equals 1, and then we need to prove that the truth of sk implies the truth of the statement sk plus 1 for every positive integer k. Now, basically what this means is we're going to show that it's true in the first case, and then that if we get to assume that it's true for the kth case, that it must be true for the k plus first case. So the way it kind of works like this is if 1 is true, and then we always show that if the next one is always true, then that means if 1 is true, then 2 is true. If 2 is true, then 3 is true. If 3 is true, then 4 is true. And it goes on, forever and ever, and proves the statement for all n. So S1, SK, SK plus 1, these are all statements. So S1 is the statement that when n equals 1, basically that we have 2 equals 1 times 1 plus 1. So I took that and I plugged in 1 there and showed that those two things equal. And so in this case, yes, that ends up being true. But that's the statement right there. And part B, let me actually do SK. So SK is just basically the exact same statement that we have here, except replace n by k. So that's saying for the kth statement, so plus 2k, that should equal k times k plus 1. And then sk plus 1 is the same thing, except we're going to go one step further. So it's 2 plus 4 plus 6 plus dot 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 plus 2k. And then we're going to go one step further, and so I'm going to go to the k plus first term of that sequence there. And that's going to equal, now replace k by k plus 1. So k plus 1 times k plus 1 plus 1. Again, you'll simplify that to k plus 2 in the future. Well, in fact, we can just do that right here. And those are the statements. So for part B, S1 is the statement that 1 cubed, not equals, I should say. S1 is 1 cubed equals, and now when I plug in 1 over here, it's going to be 1 squared times 1 plus 1 squared over 4, which is true, right? 1 times 2 squared is 4, divided by 4 is 1. So that ends up being true in this case. All right. But right now, again, we're not concerned about true or false, so we're just concerned about writing them down. So S sub k is 1 cubed plus 2 cubed plus dot 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 plus k cubed is equal to k squared, k plus 1 squared over 4. So that's basically, again, the statement, the original statement where you replace n by k, and sk plus 1 is the original statement where I replace n by k plus 1. So I just take my original, what I had for sk, and you don't even have to write this plus k cubed, but I kind of like to a lot of times. So that was sk, and I'm going to go one further. So I'm going to add k plus 1 cubed. And that's equal to k plus 1 squared. Again, plugging in k plus 1 for n up here. So k plus 1 squared, and then k plus 1 plus 1, which is k plus 2 squared over 4. All right, so let's just do an example. We've already done a lot of the work here, but so use mathematical induction to prove that 2 plus 4 plus 6 plus dot 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 plus 2n equals n times n plus 1 for all positive integers n. All right, so again, First things first, we got to check is S1 true. S1 is 2 equals 1 times 1 plus 1. So 2 equals 2. So that's true. Now, we assume SK is true. Now, um, kind of off the side, a lot of times I like to do a little bit of work here. Like what we want to show is that k plus s sub k plus 1 is true. And so what we want to show is that 2 plus 4 plus 6 plus dot 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 plus 2k plus 1 is equal to k plus 1, k plus 2. Now, we already did that up in number 1a, but I kind of like, if we hadn't done that, that's what I kind of like to write. So I know what I'm looking for. Basically, I'm trying to get to this point right here. Now, we don't get to assume this is true. We need to prove that's true. We do get to assume that SK is true. So we get to assume that 2 plus 4 plus 6 plus dot 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 plus 2k is equal to k times k plus 1. We get to assume that. That's true. Now what we got to do is somehow use that to show that sk plus 1 is true. So what I'm going to do is I'm going to add, let's go ahead and write this all down. So I'm going to add the next term, which is the k plus 1 first term. I'm going to do that to both sides. I'm working, again, I'm not using this guy up here. I'm just using sk, and then I'm going to prove that that sk plus 1 is true. So I'm just going to take what I have in this line here, and then I'm going to add to both sides. I'm going to add that 2 times k plus 1. Hopefully everybody agrees with me that that's fair, and I'm just adding the same thing to both sides. Now, notice this left side is the left-hand side of sk plus 1. Now on the right side, notice that's equal to, if we factor out a k plus 1, what's left? We've got a k, and we got that 2. So I got k plus 2, which is what we've shown. Therefore, 2 plus 4 plus 6 plus dot 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 plus 2n equals n times n plus 1 for all n. I guess I should say actually positive integers n. So that's your standard mathematical induction problem. We're going to use it again next section to prove the binomial theorem, which is kind of a useful thing to have. But yeah, the induction appears quite a lot of different places in math. So let's do this is the same as part B up here, but now we're actually going to prove it. So use mathematical induction to prove that 1 cubed plus 2 cubed plus 3 cubed, basically the sum of the first n cubes is equal to n squared plus n plus 1 squared over 4. So S1, we need to check is S1 true. Does 1 cubed equal 1 squared times 1 plus 1 squared over 4? Well, that means 1 equals 4 over 4, which is equal to 1, so that's true. So we get to assume SK is true. Let me go actually even write that. Assume SK is true. And then I want to show, and so that WTS, I use that quite a bit, want to show that, basically I want to show that 1 cubed plus dot 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 plus k plus 1 cubed equals k plus 1 squared, k plus 2 squared over 4. So I want to show that it's true where I plug in k plus 1 there, oops, and there. That's what we're trying to do. So I like to write that down so I know what my goal is, but we don't get to use that. That's just what we want to show. But so what we got to use is the original statement with just k. So sk is the statement 1 cubed plus 2 cubed plus dot 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 plus n cubed, or sorry, k cubed is equal to k squared times k plus 1 squared over 4. Now, therefore, if I add a k plus 1 cubed to both sides, so let's do that in green here. And so plus k plus 1 cubed. Now, there's different ways of doing this. You could multiply it all out, see what happens. But basically what we're going to be trying to do is we're going to try and make this guy look like this guy. Using algebra tricks and stuff like that, we want to make those look the same. Um, and so looking at this, I'm going to find a common denominator. So I get k squared times k plus 1 squared over 4 plus 4k plus 1 cubed over 4. Now notice, what do these both have in common? The first term has a k plus 1 squared, the second one has a k plus 1 cubed, so I can factor a k plus 1 squared out. And that's going to leave me with a k squared in the first one, plus a 4k plus 1 in the second one, and it's all over 4. So again, basically I took 2 k plus 1s out of here, 3 of them out of here, and that leaves me with 1 in the second term and 0 in the first term. So hopefully you can, all I did was factor there. So if you have a little bit of trouble seeing that, just keep in mind all I did was factor out a k plus 1 squared. Now looking at that, that's equal to k plus 1 squared, and then times k squared plus 4k plus 4 over 4. Well, oops. How does that numerator factor? Try and make it a little bit neater here. Well, that numerator factors to be k plus 2 squared. So k plus 1 squared, k plus 2 squared. And that over 4 can go wherever we want, so I can write it this way. So therefore, 1 cubed plus 2 cubed plus dot 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 plus n cubed equals n squared, n plus 1 squared. Over 4 for all positive integers n. All right, so last question here. Number 4, prove that 2 is a factor of n squared plus n for all positive integers n. So the first two were just showing that sums, like basically these are finite, partial sums here, looking at here. Each of the left and right side we're representing a finite sum. This one, now we got a different statement. It's that 2 is a factor of n squared plus n for all positive integers n. Now, you could prove this one you could prove without induction, but since we're just trying to get practice on using induction, let's go ahead and use that. So first off, so S1 says that 2 is a factor. 2 is a factor, if I could erase here. 2 is a factor of, and then n equals 1, so 1 squared plus 1. Well, 2 is a factor of 2. So that's true. SK, we get to assume SK, so 2 is a factor of n squared, or sorry, k squared plus k. We want to show 2 is a factor of k plus 1 squared plus k plus 1. All right. So if 2 is a factor of k squared plus k, well, let's take a look. Let's take a look at k plus 1 squared plus k plus 1. This is a little different. I'm working from here. I'm basically going to show that 2 is a factor of there. So of that. So we have um, k plus 1 squared plus k plus 1. What I'm going to try and do here is I'm going to try and get this k squared plus k as part of my as part of what I have here, because then I know 2 is a factor of that, and hopefully 2 will be clearly a factor of what's left over. So let's go ahead and multiply all this out. So I get k squared plus 2k plus 1 plus k plus 1. And before you combine things and everything like that, you might be tempted to just in your mind say k squared plus 3k plus 2. What I'm going to notice is I have my k squared here and my k here, which is, I have that right there. So that's k squared plus k. And then everything else that's left over is plus 2k plus 2. Well, notice I can rewrite that as k squared plus k plus 2k plus 1. Notice 2 is a factor because of this statement right here. 2 is a factor of k squared plus k. And as written, clearly 2 is a factor of 2 times k plus 1 because it's 2 times something, right? So, and of 2k plus 1, therefore 2 is a factor of k plus 1 squared plus k plus 1, and 2 must be a factor of n squared plus n for all positive integers n. Oops. And there you have it.